Okay, so even though I've taught the class already, I'm going to go ahead and create some videos. I'll probably go a little faster because I'm running out of time. I'm behind already. So this is class 7, and we're dealing with stuff in chapter 4, and the topic is fluid kinematics, where we talk about the material derivative, Reynolds transport theorem, and our use of control volumes. So a little cartoon that's supposed to be relevant here. One of my colleagues from the Coast Guard Academy, Dr. Andy Foley, compares the Reynolds transport theorem, or uses as an analogy, the Colosseum, where we have gladiators coming in on chariots and coming in and out of the Colosseum, where the Colosseum represents a control volume, and they're entering through control surfaces. And the chariots are mass, right? So they're the Reynolds transport. They're the thing that the mass is transferring stuff. And we just have generic things that can come in and out of the control volume. And this is really a means of trying to make a connection between the Lagrangian and the Eulerian perspectives, where a lot of times in thermodynamics, for instance, we have mass as the system, and then but in fluid mechanics we have the control volume is what we're looking at. So to try to make that system perspective and the control volume perspective agree, we consider the Reynolds transport theorem. And another diagram here where we can see that the system and the control volume aren't necessarily the same thing, but sometimes they can be, right? It's just that the system is, you could think of it as a big chunk, maybe a particle, a thing of mass that we might want to do something to. Whereas the control volume is a location, although that location can actually move, right? So we'll see a couple figures where we'll see the situations where the control volumes can actually change shape and they can move in different spots. So it's not exactly as I had shown previously with the looking at under a bridge. So let me see. I want to talk about the material derivative of something. We want to try to get the entire derivative of a thing. So we have this something we call the material derivative. And moving on to my notes here. So the idea is if we want to take the derivative of something with respect to time, that thing might also have changes in its location and its distribution with location. So if you want to get the entire derivative, we have to take it with respect to time, so the partial derivative of whatever this function is, and we call that the local. And then we also will want to have the distribution with how it changes within material space. And so we'll just take it on as an accept this for right now, but we'll take a look and see what these symbols mean. But this is called the convective. And as we saw with acceleration in the last class, I'll jump down to here, where we had the derivative of velocity, but we were taking a velocity field. So it wasn't just a single particle, but it was the field concept, where we had multiple locations. And we wanted to try to see how is that changing with respect to spot. So like in this previous slide right here, this might be something that represents a field, and this is actually the tip of a wing, and this is the vortices, a plot. It's a vector plot, so it's got a contour plot on top of it. And you can see that this has this rotation, this is not an irrotational velocity field because it has vortices. But you can see, and we're actually looking at a stationary thing, so hopefully this is like a steady flow, even though you could tell that there's dynamics taking place. Is because the velocity is different with respect to position. So we want to have velocity can change with position, and that really is the convective part of it here. So we've already looked at this, I think, in the previous class, the convective portion, and here's the local portion. But let's take a little bit of, let's see where these could also be applied. I want to come back to this right up above here and talk about the nabla symbol right here. Sometimes it's called a gradient operator. We can see what we've actually done up in here is we've dot product and I have another page where we could do the comparison of a dot product and a cross product and just multiplying it by the thing. So right here we've got the dot product. But we also previously used that for the pressure. So let's see kind of like the difference between just operating this this operator right here and taking the entire material derivative. So we can have, with other parameters, for instance, temperature or pressure, we can have, we could describe with the material derivative how those temperatures might be changing with time and also how they might be changing with position. So you can kind of see there's the velocities, and so the consequence of this symbol up here is taking the velocity and having that as part of, let's say, the dynamic temperature profile of something. Now here we go for pressure as well, and of course the temperature and the pressure are scalars. So what's interesting in this is that they could now, I'm going to take that back. I almost said that they were now vectors. Let me double check in there. Well, you don't see that any vectors in there, so I think there might be, it's an interesting thing. This is a plot. But regardless, when we come down, remember what we did with the pressure gradient, and those did become vectors right here, where we had how the pressure changes. So there's sort of a difference between the material derivative and the gradient. I'm going to actually probably have to get back to you. I think, now that I'm looking at this, I don't think this can be a vector. That's a scalar. This is this right here becomes a scalar, and multiply that there. Yeah, I think it's empty. All right. So I also, just a quick, a tour of the vorticity and irrotationality. Now, I think I brought it up maybe out of sequence here, but this right here is a velocity field that has rotationality, but solving a problem is often very difficult, and this is like a limitation for simplifications that we kind of need sometimes to be able to solve problems. So it's sort of a test that we want to run on a velocity field to see if it's rotational or irrotational. So we're going to see this, and we use the curl, where it's the Nabla operator crossed against the velocity. And as we'll see, this guy right here, zeta, is what we consider the vorticity. As a practical real world thing, if you want to find the angular velocity, it turns out to just be 1/2 of that vorticity. So this actually has some more physical meaning than this one does, or easier to appreciate, that if you want to try to figure out how fast, let's see, it's going that direction right there, that angular velocity is going to be, we could actually find the actual value for it. So this is like an idea that we want to describe vorticity. Here's actually a measure of the thing, and they just happen to be only 1/2 of the other. I put this in here probably for my own sake, because I remember being confused by this gradient, divergence, and curl type of thing. For our main purposes, the gradient, the most important one, is the pressure gradient, where we're taking and multiplying this nabla by the pressure, and that's giving us a vector, right? Where we're taking this times the scalar, and we're getting a vector, which is different from the divergence, where we're actually taking the dot product, and so this is a vector and this is a vector, and by the way, they're interchangeable, right? And so we're taking these two and we're dotting them against each other, so now we're just getting these individual things. And something really important to us in fluid mechanics, and we're not going to prove it just this moment, but this right here, if we can set the divergence of the velocity field, if that's true right there, then this is an incompressible, and this obeys incompressibility and the conservation of mass. So we're going to look at that. I think it's going to come up. I'm not sure exactly what class we're going to bring this up in, but in a later class, this is a test, right? So it's sort of an important type of thing for us if we see a velocity field, that we perform this test on it, and it'll be as part of the homework for this homework, but we'll actually have a proof for that later on. And then lastly, we have the curl, right? So we have the gradient the divergence, and now the curl of a vector field, where we take the nabla and we cross it against the velocity vector. And now the order of operations does matter, right? Because you flip the thing around. But for 3 dimensions, well, we would take the cross product. We just take the determinant of this. But most of the time we're just going to deal with 2D. So it's sort of a simple, relatively simple test to have a del V, del Y minus del U, and this should be, let me double check. I think this should be X. I think I messed this up. Someone else pointed this out in class right here. No, let me double check this here. Always good to double check yourself, and I make these mistakes all the time. So let me see, where do we have in the book for the cross product? You can probably just look and see on your own. Yeah, it's supposed to be del V, del X. Yep, and then del U, del Y. Yes, it makes sense because it's, I think it's written wrong up here too, right in there. And I bet that's going to be wrong the next time I teach the class because I'm going to forget to change it, to mix it up. But here's tests. Here's 2 tests that we can run on, and if this is equal to 0, if equal to 0, irrotational. Into, so test of if this is true right there, therefore this is incompressible. Not only incompressible, but also obeys continuity, which is to say that mass is conserved, but we can pretty much tell that's true. And then, okay, well, I already said here 2 important tests. If this is true, it's irrotational. And if the fluid's incompressible, then the divergence right here. So we often will, if we get a velocity field, amongst the things we want to do is jump to that right there and find out if it passes the test. Let me see how I'm doing with time. I got 12 minutes. Maybe I'll make another video. And then we'll do the Reynolds transport theorem as part of that. So I'll be back.